Welcome to today's episode where we'll dive deep into the Design Exchange Format, or DEF. To start, could you explain what DEF is and why it's so crucial in integrated circuit, IC design workflows?
Absolutely. DEF stands for Design Exchange Format, and it's an ASCII text file format that describes the physical layout of an IC. Think of it as the architectural blueprint for the chip, detailing where components sit and how they're connected. Without DEF, coordinating between design stages would be chaotic.
That makes sense. I've heard DEF is closely linked to another format called LEF. How do these two work together, and why is this partnership essential?
Great question. LEF, or Library Exchange Format, provides abstract info about standard cell libraries like their shapes and layers but not actual placements. DEF complements this by specifying the real-world locations and routes for each component, ensuring the design is manufacturable.
Let's move on to DEF's internal structure. What are the main elements contained within a typical DEF file, and how do they support the design process?
A DEF file outlines components, their precise placement, pin locations, signal routing, and even metal blockages. For example, it specifies whether a memory block sits in the chip's corner or center, and how signals snake through different metal layers to connect logic gates.
Interesting. You mentioned metal blockages. Could you elaborate on how DEF handles such layout constraints and why they're significant for designers?
Certainly. Metal blockages in DEF are like traffic cones in a city map, marking areas where routing can't occur due to manufacturing or performance reasons. By defining these, designers avoid signal congestion and ensure reliable chip operation, similar to planning detours in city traffic engineering.
That's a helpful analogy. What about units and hierarchy? How does DEF manage those?
DEF meticulously defines units for all dimensions, ensuring consistency across tools. It also supports hierarchical naming, letting designers reference subblocks within larger modules using divider characters, much like folders in a computer directory.
I see. Now, non-default rules or NDRs are often mentioned in DEF documentation. Could you break down what they are and when they're used in practice?
Of course! NDRs are custom routing rules for specific nets that demand, say, wider metal tracks for power or shielded routes for sensitive signals. For example, a clock net might need a thicker wire to reduce delay, and DEF lets designers specify these exceptions explicitly.
Given these sophisticated controls, how does DEF handle manual versus automated adjustments?
DEF files specify whether a component is fixed in place or can be moved by automated tools. This flexibility is vital. For instance, critical analog blocks might be locked down, while logic gates are optimized automatically for performance or area.
That's fascinating. Could you share some insights into DEF's role beyond the initial place and route, perhaps in post-layout analysis or manufacturing stages?
Certainly. After placement and routing, DEF files feed into extraction tools that analyze parasitics like unwanted capacitance impacting signal timing. Similarly, power analysis tools use DEF data to predict voltage drops, ensuring the chip won't fail under real-world workloads.
It's clear that DEF provides a comprehensive and structured way to communicate layout details. To wrap up, how has DEF influenced the evolution of chip design collaboration?
DEF has standardized layout communication across EDA tools and teams, making collaborations between global design centers frictionless. For instance, a team in California can generate a DEF file for a block and have engineers in Taiwan integrate it seamlessly, accelerating development cycles.
Thanks for these insights. For listeners new to IC design, understanding formats like DEF is foundational to grasping how modern chips come together. We appreciate you joining today's discussion.